Okay, so this is our experiment. It's actually a demonstration lab on electricity and magnetism. Okay, so let's start this off here. So we're going to talk about electricity and magnetism. And we'll see why they always come together, because they're related. In fact, one creates the other, as we'll see. So I'm going to put an arrow like this going both ways, and then magnetism. We'll do much more in magnetism in class, and of course, much more in electricity in class. But let's talk about the basics here. Excuse me. All right, so let's start from the very, very, very beginning, okay? So we're going to talk about atoms, okay? Okay, we know, most of us know, that atoms look like, this is our naive picture, look like a tiny solar system. I put this in quotes, okay? So our solar system, of course, has the Earth has the sun at the center, and the planets such as Earth orbiting. Okay, so our picture, this naive picture of the atom, is going to have something at the center, and this something at the center is what we're going to call a nucleus. Okay, we'll talk more about that later on in the semester. This is the nucleus, and the analog to the planets are going to be orbits. Oops, these are supposed to be orbits, okay? And these are going to be electrons. Okay, and we're going to see that electrons have a negative charge. They're negatively charged. And inside the nucleus are going to be positively charged protons. Okay, that's a proton. And also particles with no charge, and they're called neutrons. Okay, and so that's what's going to be inside the nucleus. Okay, we're going to be dealing with the electrons for now. Later, we'll deal with the nucleus and nuclear energy and nuclear bombs and things like that. Okay, for now, we're going to deal with electrons. And we'll see that all of chemistry is going to involve electrons going to their lowest energy state. Okay, okay. Now, let me just say a word about the nucleus, about protons and neutrons. The mass of a proton is almost the same, not quite, but almost the same as the mass of a neutron. Okay? And both of these are approximately about 2,000 times the mass of an electron. Okay, so the electrons are tiny specks. Okay, electron. So for example, if this is a 1 pound loaf of bread, okay, that would be the electron. Okay, a car, which is 2,000 pounds, would be the proton. Okay, so protons and neutrons are about 2,000 times more massive than electrons. So when we talk about the flow of electricity, we'll talk about current. It's the electrons in a metal that will be flowing, okay? Because the electrons have so little mass. They're very tiny, really little specks compared to the nucleus. So if I drew a nucleus like this, the electron would look like a dot. That would be the dot. That little dot would be the electron, okay? Very small compared to the mass of the proton, okay? So we have that picture. So atoms now, one thing we're going to say is that they're electrically neutral. Right? What does electrically neutral mean? Well, what it means is that the number of protons, the positive charges, are going to be equal to the number of negative charges, number of electrons. Okay, very simple. So if we use the word atom, atoms are always electrically neutral. The number of pluses, I'll put number of pluses here, equals the number of minuses. That means it's electrically neutral. Number plus equal to, if we have a system where the number of plus is not equal, that's not equal to the number of negative charges, these are what we call ions. Okay, so we could have positive ions, and I think you know this, plus ions are called cations, and negative ions are called anions. Okay. In the body, again, you know this from all your biology, in the body, ions, right, have a special name, right? They're called electrolytes. Okay. So we have atoms are electrically neutral. Number two, atoms are, and this is actually very amazing, mostly empty space. Isn't that crazy? Empty space. Okay, so let's talk about this for a second, because I'm sure most of you do not know this. If we look at the size of a nucleus, we take a nucleus. Now remember, this is microscopic. This is, you can't see this with the eye, but a nucleus in general, if we look at the diameter across, the distance across, it's very, very small. It's about 10 to the minus 15th of a meter. Okay, this is our nucleus. Okay, if we look at how far away in an atom the nearest electron, I'm going to put a nearest electron, there's an electron orbit, and there's our electron, okay? This distance from the nucleus to the electron is 10 to the minus 10th of a meter. Now, it's clear that this is a bigger number, 10 to the minus 10 is bigger, much larger than 10 to the minus 15th. And if I ask you how much bigger is 10 to the minus 10 than 10 to the minus 15, your first instinct is to say 5, and that's not right. That's not right at all. If we divide 10 to the minus 10 divided by 10 to the minus 15, remember our rule, 10 to the A divided by 10 to the B is 10 to the A minus B. A minus B. So this is equal to 10 to the A, which is 10 to the minus 10, minus B is negative 15, negative 15. So this is equal to 10 to the minus 10 plus 15. And that's equal to 10 to the plus 5. 10 to the 5th is equal to, right, 1 with 5 zeros. 1, 2, 3, 4, 5. That's 100,000. That means that this distance to the nearest electron is 100,000 times the size of the nucleus. So you see how far away it is. So as a simple example, we'll say suppose, just suppose, because this isn't really true, right? Suppose that the nucleus has a size, just say, of 1 centimeter. Okay, so 1 centimeter, something like this. So suppose this is my nucleus. This is my nucleus, 1 centimeter across. How far away would the nearest electron be in our imaginary atom? Well, the nearest electron would be 100,000 times that size, which is 100,000 centimeters. 100,000 centimeters is equal to 1,000 meters. 1,000 meters is approximately, it's a little more, but approximately 3,000 feet. That's a little more. It doesn't matter. But this is bigger than a half a mile. Okay. So what are we saying? We're saying if this is our nucleus, right here, here's our nucleus. Where's the nearest electron? It's a half a mile, over a half a mile away. Okay. So you see, atoms are mostly empty space. It's absolutely true. Okay. Now, what keeps the electrons in orbit? Well, what keeps the electrons in orbit is the electric force. Okay. The electric force is governed by something called Coulomb's law. Again, we'll cover this in class. And Coulomb's law looks very much like the gravitational law. And we'll talk about this in a little bit, okay? But first, let's review charges, right? We know, I think we know, we all learn this, right? That opposites attract. Opposites attract. I don't know if that's true about people, but it's certainly true about electric charges. Opposites attract. Okay, now we're going to have a picture and use our imaginations, a picture of electric forces, of electric force field lines, electric force field lines, force field lines, okay? And this whole idea was thought up a couple 100 years ago by somebody by the name of Faraday. And Faraday was a cool guy. He didn't know any math, like many of you. And all he did was experiment, and then he wrote it down in words in his notebook. So Faraday used his imagination, and his imagination allowed him to visualize what's happening with electric charges. So Faraday imagined, okay, something like this. Sorry, my pen acts up every once in a while. All right, he imagined that if you take a plus charge, there's my plus charge, okay, there's going to be an electric field coming out. Now, I can't draw an infinite number of lines, so I'm just going to draw a couple of lines, okay? Notice the arrows come out. When things come out of something, and this is a good vocabulary, we say they emanate. Emanate. To emanate is to come out of. Okay, emanate. So these electric field lines, the electric force comes out of a plus charge. And so we'd say a positive charge, plus charge, it's a plus. We would say is a source for this electric field because it's coming out. Okay, and again, these are ideas and pictures due to Faraday. Okay, for a negative charge, we have the opposite picture. So here's a negative charge, okay, an electron, if you like. And we have that the electric field lines go in. So you see they're not emanating, but they're going into a negative charge, into a negative charge. So instead of a source, we would say the negative charge is a sink, like water runs down a sink. Okay, so this would be a sink for the electric field. Okay, and this would be any negative charge. Now, if this is a proton, Just, it could be anything. And this was an electron. These are two examples of electric monopoles. Mono means one, monopoles. So an example of a positive electric monopole would be a proton. An example of a negative electric monopole would be an electron, okay? Because it's mono, it's all by itself. So if I drew an electron like this, the electric field would be going in. That was an electron. And if I had a proton here, the electric field would be coming out. See, it's a point. And so they're monopoles, okay? Now, how do they interact? Well, we said positive charge and negative charge attract each other. So if we drew the picture, here's what we draw. We draw a positive charge, say. And again, I would draw the lines coming out, emanating, right? And they really just want to keep going. They want to go all the way to infinity. They just want to keep going. Nothing's stopping them. They want to keep going, okay? And if over here I had a negative charge, well, the electric field lines want to go into it. Sorry for my imperfect negative charge here, okay? They're going like this. Now, these electric field lines want to go out, right? And they want to go to infinity, but they say, whoa, I like you better. And what they do is they get attracted, you see? And these lines want to go out. Oops, they get attracted to the negative, you see? So these lines, you'll see a picture like this. Okay, so this would be a diagram of positive and negative charge attracting each other. Okay, on the TEAS exam, on the nursing exam, if you had a charge like this and they called it A, and they had a charge like this and they called it B, and the lines were coming out, you see the arrows. When you see the arrows coming out, you know it's a positive, and if you see the arrows going in, you know it's a negative, right? And then you see this lines like this. Okay, I'm not going to fill them all in. And they say, what is A and B, right? What is A and B? Is it plus, plus, minus, 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 plus, plus, minus? Well, it's plus and minus, obviously. Okay, so that's a pretty easy picture. Okay, so that's two opposite charges attracting. And you should know this. You should know this picture. Okay, suppose I have a positive charge and another positive charge. Okay, well, we know like things don't like each other, right? So opposites attract, like repels. So these lines go like this, right? These lines are going out, going out, going out, see? And they want to go out here, and they say, ooh, I don't like you. And these lines go out, ooh, I don't like you. And you see, we have these lines of repulsion, see? With the arrows going out. So this would represent, if this was A and B, positive, positive. They repel. So that's repelling two positive charges. And we can play the same exact game, same picture with two negatives. Okay, so I just draw my lines. I'll put the arrows in a second. If I ask this on a quiz and you don't draw the arrows, it's wrong. If you don't draw the arrows, it's wrong. Once more, if you don't draw the arrows, it's wrong. So this would be a wrong picture, even if I did this, okay? Even if I showed that they repelled, okay? This is wrong, okay? You have to show me the arrows. Well, this is negative. It's a sink, so all the arrows are going in. All the arrows going in, the arrows going in. So now the picture is correct. Okay. It's exactly the same as the two positive charges repelling, the one on the left, except the arrows are going in instead of out. Okay, so you need to know these pictures, okay? Again, not the hardest thing in the world. Okay. So we said we're going to talk about the motion of electricity. Okay, so in order for electricity to flow, right, electricity is going to involve the flow. We can say current, we'll just say the flow of electric charge. Okay. Now in lab, we're going to take some table salt. And again, we'll learn about table salt and these chemical formulas later in chemistry. But table salt that you put on your food is given by sodium, Na, with chlorine, Cl, right? NaCl. So this is called sodium chloride. Okay. Now, if I have a circuit, suppose I have a battery. Okay. And I plug it in. There's my light bulb. And I connect this. The electricity is going to flow. The electron's going to flow and complete the circuit and make this light bulb flow. Okay. If I take my battery here, okay, again, D. Now, if I take my wires, okay, and if I want to connect them, I'll put a light bulb here again, okay? If I take one of these, okay, and I put it on a piece of salt, and then I take this. So this is a salt crystal, NaCl crystal, NaCl crystal. Now, the electricity wants to flow, wants to go from one end of the battery to the other, but when it hits this crystal, nothing happens. The electricity, charge, does not flow through here. And so the light bulb is dark because there's no current. Okay, now if I take the same thing, same salt, okay, now I'm going to take my battery. I'm going to take out battery like this, same thing. Okay, put a little thing there, put a little thing there, take the wire. All right, take the wire. Again, I'll put this by a light bulb. Oopsie. Okay, there's my light bulb. I'm going to take this wire, and now I'm going to put it in this tank with water, with salt water. Now, in water, the sodium, remember, salt was Na and Cl. When you make this aqueous, put it in water. Okay, that means put it in water. What happens is this thing breaks up. I'm going to put an arrow going this way, an arrow going this, and it breaks up into a sodium ion, like you have in your body, the electrolyte, and a chlorine ion. So now what you have in here are Na ions and Cl minus ions. Now, when we put these two things in here, the electricity can flow through this salt water because of the presence of ions. Okay, the solid salt does not conduct electricity because the NaCl did not break up into ions. Okay. And so you won't get a flow of electricity. So to have electricity flow, you need the flow of charged particles. Solid salt does not have free particles, free ions moving. Okay. Now let's talk about static electricity for a second. It's called static electricity. Essentially, we've all felt this, right? Right? When you walk, just you walking. Now, if this is a rug, carpet, and you rub your feet across there, and then you go to the door, and you're going to touch this piece of metal, the metal doorknob, What happens is when you touch that, zap. Sometimes you get a shock. Okay? That's called static electricity. And what you're doing when you walk across the rug is you're essentially ripping off electrons. Ripping off electrons. Okay? So that means you become charged. You become, if you lose electrons, you become positively charged. Now, when you touch this metal doorknob, it turns out metals have electrons that like to move. They have electrons that like to move. Electrons that like. That's why metals conduct electricity, like to move around. So now if you touch this metal doorknob and you have a positive charge, what do those electrons want to do? They want to go to where the positive charge is, and you get a shock. Okay, that's static electricity. Okay, whenever you have a plus on one end and a minus on the other, there's going to be an attraction. There's going to be something going on. Okay, now in the lab, there's a device that we use, and it's called a Hofmann apparatus. Hofmann, German, Hofmann apparatus. Okay, now this is a device that uses a process called electrolysis. Okay, and what we're going to do is we're going to zap some water. Zap water with electricity. Now, the electricity, this is a very simple idea, right? The electricity has energy. And most of us know that water is this. It's two hydrogens, H2O. And this is a water molecule, okay? If you add energy, electric energy, what can happen is you can break up this molecule. Break up the water molecule. And when you break it up, what do you get? You get H2, gas. And it turns out you're going to get an O2 gas. Okay. Okay. So you break them up and you can burn this. This burns nice, right? Since there's two hydrogens to one oxygen, the volume of hydrogen gas should be 2 times the amount of oxygen gas when you do the electrolysis, right? Because there's twice as much hydrogen as oxygen. Okay, so this is called the Hofmann apparatus. And then again, you could use this hydrogen gas, you could burn it. And if you burn it, you add oxygen, you just get water back. Okay, so hydrogen would be a good fuel. Oxygen, pure oxygen, man, it's really dangerous stuff. Okay. The second device we have in lab is something called a Van de Graaff generator. Van de Graaff generator. Okay, a Van de Graaff generator is just a big static electricity generator. Remember when you walk across the carpet? Remember this? Remember you walking across the carpet? Do, 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 do. And if you walk on the carpet, what you're doing is you strip away electrons. Right? You end up with a big positive charge. Okay. A Van de Graaff generator has a huge belt, has a belt. right? And it's going to rub against something. It doesn't matter against something. It doesn't matter what it is. And just like with you walking across the carpet, we're gonna strip away electrons. Okay. And then you get a big voltage, right? We'll talk about voltage later. But the voltage in some of these devices, one can get up to something like 100,000 volts. Okay. Sometimes, so the Van de Graaff generator is something like this. We have this huge ball thing here, and there's a belt going around in here generating electric charge, and this is a metal sphere, right? This is a metal sphere. That gets all charged up, probably, okay? And what happens is sometimes we would put a student on a box, okay? So they're not touching anything, and they come here, okay? And what happens is they have their hair. Is their beautiful, clean hair. If they keep their, oopsie, sorry, the pen, a little crazy. If they keep their hand, don't take your hand off, keep their hand here. What happens is they're going to get all charged up, okay, positively charged. And what happens is your hair, if this hair has a certain charge plus, and this hair has a plus, and this hair all has plus. What happens is your hair starts pushing away from each other because they all hate each other, right? So what happens is the student's hair stands up. It's all so cool. Isn't that cool? Okay. So a Van de Graaff generator is a device used for generating very, very, very high voltages, right? By using static electricity. Okay. All right. Now, a couple words about current. And this doesn't have to do with electric current, but any kind of current. The current of anything is the amount of stuff flowing divided by the time to flow. So this is current of anything. So if I look at water, okay, so suppose we have a hose. There's my hose, and the water's coming out, and it's going to fill a bucket. All right, and my amount of water is 3 buckets per minute. Well, that's the current of water. Current of water. There's the amount, 3 buckets, and there's the time. So that would be the current of water. If we talk about electric current, it's the same idea. Electric current, we give the symbol I. I'm not sure why they give it. And this is just going to be the amount of electric charge flowing, amount of electric charge flowing divided by the time it takes to flow. I'm just going to put time to flow. Here's where we'll talk about some units, all right? So electric charge, Q, is going to be called electric charge. That's the symbol we use for electric charge. And we have to give it a unit, and the unit's going to be called a Coulomb. Well, Coulomb's the one who studied this stuff. Okay, so The amount of electric charge flowing is Q. The time is T. Okay. So this is usually measured in seconds. So Coulomb per second is the unit of electric current, I. And this unit is called, you might have heard of it, an ampere, amps. So what is an ampere? It's how much electric charge is flowing in a given time. Okay, now I'm going to take a step backwards. Remember I said the electric force between any two positives, two negatives, a positive and negative, doesn't matter. The electric force was given by something called Coulomb's law. I didn't tell you what Coulomb's law was. Coulomb's. That's an M. Coulomb's law. Okay? And it looks very similar. It's not the same, but very similar to Newton's universal law of gravity. I'm just going to put law of gravitation. Remember, if we have a mass M1, that could be the sun, mass M2, that could be the earth, or M1 could be your pocketbook, M2 could be the kitchen table, M1 could be the refrigerator, M2 could be a taxi cab on Madison. It doesn't matter. Any two masses. And if they're separated by a distance d, then we said the gravitational force, F gravity, was equal to, there's some constant. We don't worry about this in this course. It's just a gravitational constant. But take the mass of one object, take the mass of the other object, and divide it by the distance squared. Remember, we said this was an inverse square law. So this law of gravitation is an example of an inverse square law. Square law. Okay, that was Newton's law of gravity. Now, Coulomb's law says this. Well, if there's a charge here, call it Q1, and there's a charge over here, call it Q2. Again, this could be a proton, electron, it doesn't matter, right? And they're separated by a distance d, then the electric force, F electric, is equal to, here's another constant, K. Okay, this is called the electric constant. We don't need it for anything we do. This is the electric constant. Okay. G was the gravitational constant. Grav constant. Gravitational constant. Okay. And now we take the product of Q1 times Q2 divided by d squared. So you see, this is also an inverse square law. And it looks very much just same form as Newton's law of gravity, right? They look very much alike. Q1, Q2 over d squared. Here we have M1, M2 over d squared. Okay, and all the forces are measured in newtons, right? Newtons. Okay. So we have the electric current. And again, well, we're not going to get into it right now, but remember, I've been talking about a battery. A battery is essentially this. Battery really has two sides to it. And there's actually two different chemicals in it. And one side has a very high energy state. And the other side has very low energy state. Okay. Now, when we take a wire, right? Remember, a wire is made of metal, right? This is a wire, and it's metal. And I said before that in metals, electrons like to move around. Well, if you connect this wire to a high energy state, and then we're going to put something in the way, like a light bulb, because it's easy for me to draw, kind of, okay? And this is the low energy state. Well, what do the electrons want to do? Well, electrons want to go from a high energy state to a low energy state, right? If I have a ball on top of a table, right, and it rolls, it's not going to stay there. It's going to go to a lower energy state. Well, electrons want to go to a lower energy state. And while they go to a lower energy state, we make them do some work because those electrons are not so smart. And when they go through here, and you could imagine that the light bulb heats up, so you get heat and light out of this, right? And it heats up because it's just like when you take your hands and you rub them together. What you get is friction and heat. Now, when this friction occurs, what happens is it starts to glow, and we get light. So these dumb electrons, we got them to do work because they wanted to go from a high energy state to a low energy state. Now, this side, if it keeps giving away energy, it's going to lose energy, lose energy, lose energy, lose energy until the energy on this side is exactly equal to the energy on that side. And when that happens, the battery is dead, right? Dead, 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 dead. Okay, because electrons won't go from the same state on one side to the other side, right? It has to go from a high state to a low energy state, right? Some batteries are rechargeable. You can get this back up to a high energy state, all right? And we usually determine how much energy, the energy difference, in something called volts, right? Voltage. V, we measure those in volts, okay? And no, that's the thing that makes the current. It's like a pump. Right? It's like an electric pump. Like you have a water pump, it's like an electric pump. It gets the charges to flow, forces charge to flow, forces charge to flow. Okay. And then we said, well, remember, it heats up. Remember the bulb heats up? Heats up. Why? Because of friction. So the electrons don't move smoothly through the metal. They meet up with friction, and we call this friction resistance. Okay, once again, we'll do more of this in class or in the YouTube videos you can watch. Okay, so now we have electric current I, electric potential difference V, and the resistance R, and they're all related. And this is a very important equation for the T's, and it's the simplest equation. They're related by something called Ohm's law. And it's given by this, V equals I R. Okay. And so if we solve for R is equal to V over I. So what are the units of R? Well, this would be volts. Remember, electric current was called an ampere. So resistance is measured in volts per ampere. And this name, this unit is given a name. It's called an ohm. So resistance is going to be measured in ohms. Okay, and we're going to give that this symbol, omega. Okay, so for example, if I took about 50 ohms, a resistor has 50 ohms, we would, on a test or in everything we do, this would be written as 50 ohms with that symbol. Okay, all right, no more math here, no more math. Okay, let's say a couple of words about magnetism. Okay, and I'm not going to get into the whole thing here. We will do it more in class, but let's talk about magnetism because they're related. Okay, first, let's talk about a permanent magnet before I talk about anything permanent magnet. Like we have in lab, like you probably have in your house, some of you. Okay, we have a magnet, and most of you may know, I'm just going to draw a magnet like this, that we don't talk about plus and minus for magnets. We talk about the poles, right? And we say there's two poles. And we don't call them plus and minus, right? We call one pole north. And again, I don't know the historic reasons for this. And the other one, south. Okay. They're similar in one sense to our picture that Faraday gave us. So again, we're going to Faraday to do our picture. And for Faraday, lines emanate, remember that word, emanate, come out of the North Pole, come out of the North Pole, come out of the North Pole, come out of the North Pole. And for this thing, we can draw these lines circling back. Oops, sorry. Sorry, my pen is doing crazy things. And we draw these lines, doing something like this, going in to the south. See these lines? Like this, okay? So again, my pen is a little strange, okay? So the lines go in to the south pole and out of the north, okay? And this then would be called a magnetic, because there's two poles. This is called a dipole, two. Magnetic monopoles do not exist. Magnetic monopoles do not exist. We've never seen them anyway. Magnetic monopoles do not exist. What do I mean? They don't exist. In other words, you will never see a North Pole all by itself putting out field. See that? See that's coming out. See that's coming out? Never. We never see this. Never. We never see a South Pole all by itself with the fields going in. We never see that. No magnetic monopoles. We always see a dipole. And again, we have the same rule that we followed for electricity, that opposites attract. And the same poles would repel. So if I said, show me a attraction of a north and a south pole, if I asked this on a test, here's a south pole, here's a north pole, and then I put another magnet here. And if this was a south and this was a north, well, these lines come out of the north and into the south. You see, that's the attraction. There's attraction. There's the attraction. Okay, and of course, some of these lines do circle around and come back there and come back around. Whee! Oopsie, something like that. And these lines come out and will go in there also. Okay, something like this. But the important thing I want to show is that the north here, the lines are going in to the south, in to the south, in to the south. See? So that would be attraction, right? Opposites attract. And if I had two north poles, for example, same picture, put a south there and a north, and then now put a north here and a south. Well, these guys hate each other. So the lines want to come out and say, I hate you. Their lines come out and say, oh yeah, I hate you. And so we'd have lines that look like this. Okay. Hopefully everybody can see that. And now if we want to do the two south poles, again, it would be the same exact picture, right? We would have this. Oopsie. So here I'd put a north, and here I'd put a south, and here I'd put a south, and here I'd put a north. Okay, and again, these lines look the same. They come like this, they come like this, they come like this, they come like this, like this, like this. But again, without the arrows, that's wrong. So you got to show me the arrows. These are south poles, so they're going in, in, okay? Same picture as the north picture, right? North and north, except for the arrows, the direction of the arrows. Without the arrows, then the picture's wrong, okay? So you must have the arrows, okay? And finally, I'll just say a couple words because we're going to spend a lot of time on this. But I do want to mention this because you never know what'll appear on a quiz, right? You never know. I want to say that all magnetic fields, not some, all magnetic fields come from, and I could use different words here. I don't care. Well, I could say moving, or I could say accelerating. I'll accept any of these, accelerating. And a lot of times I use the word wiggling. You'll see what I mean in a second. Wiggling. Electric charges. So that's why we always do electricity and magnetism together, because all magnetic fields come from moving electric charges. All magnetic fields come. And this is where I'll just say a couple more words. Okay? Let's say we have a plus charge. Okay? I'm just going to take a plus charge. And it's static. So it's just sitting there. I'm just going to draw a couple of lines coming out. Okay? And I imagine these are the Faraday lines, right? Faraday imagined these lines coming out. I imagine these lines to be something like jump ropes, just standing there, right? Okay? Just sitting there. So this is static. Nothing happening. And this is the electric field, right? That's the electric field. Coming out, emanating from the positive charge, electric field. Okay, no magnetic field, nothing happening. Now, suppose I take this charge now, and suppose I starts to wiggle it. Okay, now think of think of a jump rope. You start wiggling. So I'm going to take this charge and I'm going to say wiggle it up and down, wiggle it up and down. Well, what happens is these electric field lines that are coming out, they start to wiggle. So now I'm going to have this wiggling electric field. Sorry, it looks spastic, but okay, it doesn't matter. Okay, so this is our wiggling electric field. You can say oscillating, okay? So WEF means wiggling electric field, wiggling. And in parentheses, I'll put oscillating if you want to impress your friends, oscillating electric field. Okay. Now, it's a fact of nature. This is the way the world is, that when you take a wiggling electric field, what it produces is, oopsie, it produces now a wiggling magnetic field. Okay, so WMF is a wiggling. Again, you can say oscillating if it makes you happy. Oscillating magnetic field. Okay. So what we're saying is that a wiggling or oscillating electric field produces an oscillating or wiggling magnetic field. But the story's not over, because now it turns out that this wiggling magnetic field is going to produce a wiggling electric field. But remember, the wiggling electric field produces, oopsie, a wiggling magnetic field. So our schematic here is this: a wiggling electric field, oscillating electric field, produces an oscillating or wiggling magnetic field. But the wiggling magnetic field produces a wiggling electric field. But the wiggling electric field produces a wiggling magnetic field. But the wiggling magnetic field produces a wiggling electric field. But the okay, you get the idea, right? So together, what we produce is a wiggling or oscillating electric field. And we get a wiggling magnetic field because they each produce each other, wiggling magnetic field. Together, this is called electromagnetic. See, electric and magnetic together, magnetic radiation. Okay? And it's going to see, you see, again, imagine I'm standing here and there's your sister, okay? And you have a jump rope. And now you start wiggling the jump rope. Wee, wee. When you wiggle it, you put energy in. You're putting energy in. Right? When you wiggle a jump rope, you put energy. If you wiggle it really fast, really fast, then you put more energy in. So it turns out this electromagnetic radiation, the energy is going to be proportional to the frequency. What do I mean by the frequency? What I mean by the frequency is how fast you wiggle it. Fast, you wiggle the charge. You wiggle the charge or oscillate the charge. If you wiggle it really fast, you put a lot of energy in and you'll get electromagnetic energy, radiation with a lot of energy. How fast you wiggle the electric charge, electric charge. So you produce electromagnetic. If you wiggle the electric charge slowly, or you can take a magnet and wiggle it slowly, you produce electromagnetic radiation. If you wiggle it slowly, the electromagnetic radiation does not have much energy. If you wiggle it a little faster, then the electromagnetic energy will have more energy because you're putting more energy in. And if you wiggle it super fast, you'll get electromagnetic radiation with a lot of energy. So we get EM radiation. Okay, electromagnetic radiation is wiggling electric fields and wiggling magnetic fields. Okay, and just quickly, if and we'll go over this, we produce what's called the electromagnetic spectrum. We'll spend a lot more time on this, but it's good that you hear it more than once, magnetic spectrum. Remember what we said. The faster you wiggle the charge, the more energy it has. So the greater the frequency, the more energy it has. So if this is a small frequency, remember we said that's small energy. If you wiggle a charge, it doesn't have much energy. Well, this part of the spectrum, the EM spectrum, okay, is called radio waves. So your AM and FM, right? Those waves, if you put a radio on right in your house right now, you can pick up a station. That means those radio waves are passing right through your body right now, but they're not hurting you because the frequency is small, and so the energy is small, not hurting. Now, if you take electric charge, right, and this is WKBC, radio station. What they're doing is they're taking electric charges, plus or minus, and they're wiggling them, and they're putting out wiggling electric fields, right? But they're also putting out wiggling magnetic fields. If that's your house, right, and these things come in, radio waves get right through. Okay, they come to you. Now, if the radio station, WKBC, wiggles those charges a little faster, they get more energy out, and you get something called a microwave. Okay, electromagnetic. And if they wiggle it even faster, here we're going to increase the frequency. Remember, if we increase the frequency, how fast we wiggle, we're also going to increase the energy. Right? Again, think of the jump rope. The faster you wiggle it, the more energy you put in. Okay, so microwaves have more energy than radio waves. Okay, and if we wiggle it really faster, if WKBC wiggled their charges faster, they would get something called infrared radiation. And that's also called heat. So another name for infrared radiation is heat. So when you feel heat, it's really infrared radiation. Now I'm going to leave a little gap here. Okay, we'll come back to that. Now, if you keep wiggling it faster and faster, increase the frequency, right? Then we get what's called ultraviolet radiation, right? The stuff that gives you skin cancer, ultraviolet radiation, okay? And if you wiggle it faster, faster than that, you get more energy, and that's what we call an X-ray. Okay, notice it has more energy than ultraviolet, has more energy than a microwave or a radio wave or heat. And if you wiggle it the fastest you can wiggle it, the highest energy you can give it, this is called gamma radiation. Okay. So what is gamma radiation? It's wiggling electric fields and wiggling or oscillating magnetic fields. What is an X-ray? It's wiggling electric fields and wiggling magnetic. What is ultraviolet radiation? It's wiggling electric fields, wiggling magnetic. What is heat? It's wiggling electric fields, wiggling magnetic. What is a microwave? It's wiggling electric fields and wiggling magnetic fields. What's a radio wave? It's wiggling electric fields and wiggling magnetic fields. What's the difference? The difference is how fast they wiggle. Okay. Now in this gap here, we have our old friend Roy G. Biv. These are the colors of the spectrum. So here is visible light. So red, orange, yellow, green, blue, that's an I in there, indigo, and violet. So violet, which is on closer to the sun, has the most energy. So purple light or violet light has more energy than red light. Okay. So what is visible light? When you look with your eyes, when you see things, what do you look? Visible light is wiggling electric fields and wiggling magnetic fields. What is an X-ray? Wiggling electric fields and wiggling magnetic. They're all part of the electromagnetic spectrum. Okay. So again, we'll go into more detail with this, but remember, all magnetic fields are produced by moving, accelerating, wiggling, oscillating, whatever you want to say, but moving electric charges. You cannot have a magnetic field without moving electric charges. And just very, very quickly, if we talk about the Earth very quickly, we know the Earth has a magnetic field. Right? This is the Earth. We say, oh, there's the North Pole and there's the South Pole. And we take a compass needle, it's going to point, right? Why does the Earth have a magnetic field? Because in the center, in the core, it's very hot. And what happens is the metals break up. Remember, atoms are electrically neutral. So what you have is plus and minus charges, plus and minus, plus and minus, plus. But it's rotating. So in the center of the Earth, we have rotating or moving electric charges. And we know the Earth's magnetic field flip-flops every 40,000 years or something, but we don't know why it flip-flops. So we have rotating or moving electric charges. in the core. In the Earth's core. And these produce, the magnetic field, produce Earth's magnetic field. Earth's magnetic field. So again, all magnetic fields come from moving electric charges. In class, I'll tell you how a magnet that we have in lab with the south and the north, remember we have this bar magnet. Don't forget, it's a dipole, not a monopole, right? Okay, so I have to show you that somehow there's moving electric charges here, moving electric charges. So I'll do that in class. Okay, so that's enough for this session. This is kind of the background. Okay, take care.